And staying with this notion of increasing and decreasing, when a curve is increasing, dy dx is greater than 0, and the slope is greater than 0. Slope is positive when it's increasing, and when a curve is decreasing, dy dx, or the slope is less than 0, it's negative. Positive there, negative there. So an example around this then, for what values of x is the curve increasing? Okay, so if the curve's increasing, dy dx is greater than 0. Okay, so y equals 2x squared plus 8x minus 5. Dy dx equals 4x plus 8. And that means that 4x plus 8 is greater than 0. 4x is greater than minus 8 because it crosses over the bridge. So x is greater than minus 2. This curve is increasing for all values of x that are greater than minus 2. Okay, this bit of theory now again to do with graphical representation of the slope function. So we're going to try and visualize it now if you like. So let's take the function y equals x squared minus 2x minus 3, and let's say that that looks like this. Okay, and let's differentiate that function to find the slope derived or sloped function, and that's 2x minus 2. And let's say we plot that as well. Okay, and it's just interesting to note that where from point A to B, this is decreasing, and from A to B, this part of this slope function is under the line, it's negative. Okay, and from B to C on this curve, it's increasing, and its corresponding slope function is positive, it's above the x-axis. Okay, and also where if we were to get the slope at point B here, that's 0, okay, and that's 0 here on the y-axis, it's 0 there, okay, where it cuts the x-axis. So just, the slope function replicates, if you like, the increasing and decreasing and positive and negative negative nature of the slope function replicates the positive, negative, increasing, decreasing nature of the curve. And similarly, if we had a cubic function, it's in positive, increasing there, positive, negative, and if we were to differentiate y, and we differentiated that, we'd get a quadratic curve, a parabola, and again, from here to here is positive, and it's positive there. Okay, from there it's decreasing to here, and it's decreasing here as well. Okay, and from 2 onwards it's increasing, and from 2 onwards its slope function is increasing as well. So it's just to note how they follow each other in terms of positive and negative, increasing and decreasing. The function and its slope function, if we were to look at them graphically or represent them on a graph. So here's an example in connection with graphical representation. So it's on page 524. Here we have a curve, it's a graph of a quant function, okay, and it cuts the x-axis at 3 and minus 1, and x equals 1 is the minimum turning point. So if we knew what that quadratic was, and we got its derivative or slope function, or found dy dx, and we were to plot that, which of these would it be? Okay, well the answer is it would be B, because x is greater than 1 on both slopes. Both slopes are positive, for values of x greater than 1. So x is greater than 1, that's positive, and that's x is 1, that's positive as well. And the second point is for x less than 1, so that's going this way, x less than 1, the slope of the curve is negative, so it's definitely negative there, and for x less than 1, 1 is there, yes, it is negative, okay, and then at x is equal to 1, that's here, the slope of the curve is 0, slope of the curve there cuts the 0 on the y-axis at x equals 1. So this is the correct slope function for that graph based on looking at the points where it cuts the axis and where is it positive or negative at those points. Okay, so now we're going to move on and we're going to talk about rates of change. So if dy dx, let's say that was equal to 2, that means that y increases by 2 units for every 1 unit that x increases. And for linear equations, this represents the rate of change of y with respect to x. And it says that it's constant. It's always going to be 2. Every unit of 1, it will rise to 1, 2, 1, 2, all the way. Okay. So let's consider a car, okay, and let's have time going this way and distance that way. And let's say the car travels 60 kilometers at constant speed in 1 hour, okay? So if we were to plot that, it would be a straight line. The slope of which would be the rise would be 60 over the run as 1. 60 kilometers per hour, constant speed, nice straight line, okay? And so what we're saying there is that the distance y increase by 60 kilometers for each hour, each unit change in x, okay? Now, that's all well and good, but we don't travel at constant speeds all the time. Most of us travel at different speeds, and that's represented by this curved line here. Okay? It's not a constant slope. But we can work out the average speed for this changeable speed over an hour, because we can just say from A to D, we can find the slope of that line, and we can see that the distance covered, the rise over the run, is 30 over 1, is 30 kilometers per hour. Okay. It's 30 kilometers per hour. And, this 30 is also the slope, or it is the slope, obviously, of OD, the line OD. Okay. If we want to know the average speed between B and C, so now we're going into kind of curved territory now, we're not on nice straight lines, we can join B and C and find the slope of that line that joins the 2 points, and that will give us the average speed, which is kind of what we did from 0 to D earlier. Okay? And this would give us the average rate of change. But let's say we wanted to find the instantaneous rate of change, okay? So what is it at a particular moment in time? Okay, we'll move off the other graph and we'll just start with a fresh graph here. And let's say, it's distance, time, and we have this curve. But, if we want to find the average speed between 2 points P and Q, we join them and we find the slope of that line for the average. But for the instantaneous rate of change, say at P, what is the speed at P? Not between P and Q, but at P itself. Well, we can do that by getting the slope of the tangent to the curve, slope of this tangent here to the curve at P, by finding dy dx of the bigger function, dy dx, and letting x equal 1. So we find dy dx and plug x equals 1, and we'll be able to find the instantaneous rate of change at that time, the speed at that time. So dy dx would be equal to the instant speed, not the average, at that particular point in time at x equals 1, say. Okay, so there's our point, there's our tangent. Dy dx gives us the slope. Plug it in and we get a slope value equal to whatever it is.